In this video, we're going to use the node voltage method to find the current IO, which is the current flowing through this 2K resistor here in this direction. Now, because we're going to use the node voltage method, the first thing we want to do is to identify all of the essential nodes. So we know this is going to be an essential node here. I'm going to label this 1. This is another essential node. I'm going to label this 2. This is an essential node. I'm going to label this 3. And we have one more essential node down here. And I'm not going to label it because I'm actually going to take that bottom node as my reference node. Now we know we're going to be using the node voltage method. So we want the voltage at each node. So I'm just going to write V at each node, which is going to stand for the voltage. Now we know the ground node or the reference node has a voltage of 0 volts, right? So let's continue. Now what we want to do is we want to write the node voltage equations at each node. I'm going to start at node 1, which is this node right here. So I'm going to say node voltage at node 1. Now we're going to assume the current is leaving the node, right? So in this branch here, we're going to assume the current is going this way. So because we have a current source that's actually entering the node, instead of it being a positive current, is actually going to be a negative current. So we're going to have negative 4 times 10 to the negative 3 plus, we're going to assume the current is going in this direction here. So we're going to take the difference of the voltages V1 and V2 and divide it by the resistance to find the current. And because the value of that resistor is 1K, we're going to write it over 1000. Plus, we have the current going in this direction. So that's going to be plus V1 minus V3 divided by the resistance, which is a 1K. So we're going to have 1000. And all of that equals 0. Right? So when we start to simplify this now, we know the LTD is going to be 1000. So we're going to multiply each term by 1000 to get rid of the denominator. When we multiply the first term by 1000, we're going to get negative 4 plus V1 minus V2 plus V1 minus V3. And all of that equals 0. So when we simplify this, we're going to get 2V1 minus V2 minus V3 equals 4. So this is equation 1. Okay, now let's do a node voltage equation for node 2, which is the middle node right here. So we have node voltage at node 2. So we're going to assume once again that the current is leaving the node. So it's going to go in this direction, and this direction. So for the current going in this direction here, we're going to take the difference of these two voltages and divide it by the resistor, which is 1000. So we're going to have V2 minus V1 over 1000 plus, now we have the current in this direction here. As we can see, when we look at this, we just have a voltage source, right? Now this is the first time I think I've done a problem like this where we just have a voltage source. But when you have this voltage source with no resistor in between, guess what that means? This voltage source, the value of that voltage is going to be the same voltage at that particular node. Therefore, we don't even have to write a node voltage equation for node 2. Why? Because we have a voltage source, which means this voltage right here is going to be the same voltage at node 2. Therefore, we know V2, I'm just actually going to cross this out, right? We know V2, which is the voltage at node 2, equals the value of that voltage source. But pay close attention to something. This is going to be 6 volts, right? But look at the polarity. The polarity is a voltage rise from negative to positive, which means this is actually going to be a negative voltage, right? So instead of it being just positive 6, we're going to write it as V2 equals negative 6 volts. Okay? I'm actually just going to circle that. So that's very important that we saw that. Now, let's continue. So we wrote a node equation for node 1. So we can actually substitute in this value into this equation and simplify equation 1 further. So I'm actually going to do that. Let me just erase this. So I'm going to have 2V1 minus V2 is going to be negative 6 minus V3 equals 4. When we solve this now, we're going to get 2V1 plus 6 minus V3 equals 4, which is going to give us 2V1 minus V3 equals negative 2. So this is going to be our updated equation 1. Okay? Now let's do the node voltage for node 3. Remember, we're going to assume the current is going to leave this particular node. So we can write node voltage at node 3. So because we have a current source that's going to be leaving this node, we know it's going to be a positive 2 milliamps. So we have 2 times 10 to the negative 3 plus, now we have V3 minus this node, and we know the value of this node is negative 6 volts, right? So because we know that, we can write it as V3 minus negative 6, which is V2, divided by the resistance, which is going to be 2000. Plus, we have V3 minus V1 divided by 1000. We know the LCD is going to be 2000, so we're going to multiply each term by 2000. 2000 by the first term is going to give us 4 plus V3 plus 6 plus 2V3 minus 2V1 equals 0. Right? So when we start to simplify this now, we're going to get negative 2V1 plus 3V3 equals negative 10. Now when we look at this, we have two equations, right? Let me just label this as equation 2. We have two equations and two unknowns, and we have the same exact unknowns, so we can just use matrix multiplication, right? Now for the first term, I have 2V1 minus V3, so I have 2 minus 1. We know the unknowns are going to be V1 and V3 equals, that's going to be negative 2 for the first equation. Now for our second equation, we have negative 2V1 and we have positive 3V3, and that equals negative 10. So using our calculators, we're going to take the inverse of matrix A and multiply it by B. When we do that, we're going to get V1 equals negative 4 volts and V2 equals negative 6 volts. Now they want us to find the current, IO, which is going to be the current flowing through this branch here, which is going to be the current flowing through this resistor here, right? Now because the current is flowing in this direction, we know the current usually flows through the positive terminal and out the negative terminal. So we're going to assume it's a voltage drop here. Therefore, to find the current, we're just going to use Ohm's law, which is going to be V2 minus V3. That's going to give us the voltage across this 2K divided by the resistor, which is 2000. So we have IO equals V2 minus V3 divided by the resistance, which we know is going to be 2000, right? And we saw how we were able to say which one was going to come first. Because the current is flowing in this direction, we know it's going to be a voltage drop, positive to negative, which means we're going to start at V2 and then subtract from V3. All right, so V2 in this particular situation we found to be negative 6 volts. So we know IO equals negative 6 minus, I made a mistake. So we know this isn't V2, this is actually V3, right? Because we found the unknowns V1 and V3. So we know V3 is going to be negative 6 as well. So we have minus negative 6 divided by 2000, right? So when we solve for this now, IO equals negative 6 plus 6 divided by 2000, which means IO equals 0 over 2000. Therefore, we know the current IO is going to be 0 amps. So this is going to be our answer for this particular problem. IO equals 0 amps. So there is no current flowing through this resistor. Now you might be wondering, how is that possible? Well, let's take a look at this circuit. We have two current sources. Now the bigger current source is going to be this current source here. So let's just try to follow the flow of current for a second. So this current is going to come to this node here. Once it comes to this node, it's going to split two ways. It can go this way and it can go this way, right? So some of the current is going to go this way and some is going to go this way. Now, because it's a 1K, I'm going to assume that 2 milliamp of current is going to go this way, 2 milliamp of current is going to go this way, right? But that don't really matter. Let's just follow the current here. Now, once the current comes up this way, it's now going to come down here, right? So the current that went up this way is going to come to this node here. Now, the current that comes to this node here has two options. It can either go this way or it can flow this way. Let's look at this. Which way do you think that current is going to flow? Well, we know this branch has a resistor. This branch has no resistor. Current is always going to take the path of least resistance, which means that the current is not going to flow through this 2K resistor, but all of that current is actually going to come down here. So we know no current from this branch is going to go this way. None. So, of course, I just said I'm going to assume 2 milliamp of current is actually going to come this way because of this 4 milliamp of current, and we have a 1K and a 1K, which means they're going to split equally. So that's where this 2 milliamp of current is going to come from, right? Now, when we look at this 2 milliamp of current that's going to come this way, we know once it reaches this node, it has two options. It can either go this way or it can come through this 6-volt source. Well, guess where it's going to go? It's going to go through the path of least resistance, which means all of the current that's going to flow through this 1K resistor here, once it reaches this node, is actually just going to decide to actually come down this voltage source because it does not want to travel through this 2K resistor, which means all of that current is now going to go this way, which means no current is actually going to go through this 2K resistor. Therefore, our calculations, when we calculated for the current IO and we got 0 amps, is accurate because no current is going to flow through this resistor. Current is always going to take the path of least resistance. So IO in this circuit equals 0 amps.